All right, welcome back to our asynchronous assignment. This is week 7. Today we're going to be very heavily focused on solving trig equations, such as the one that you can see down here. Now, this trig equation is quite complicated. It's got many features to it. It has a lot of steps that you're going to need to take to solve it. This is not what we're going to start with. We're going to start with something that's a bit more simple, and we're going to work our way up towards this type of a problem. So let's get started. What are our learning objectives for today? Today, we're going to be learning to evaluate inverse trigonometry with the unit circle. And when we're doing that, we're going to always work to identify multiple solutions. Remember, guys, when you do inverse trig, it's very common for there to be more than one solution, since we've observed already that many angles can give you the same evaluations in your trig functions. For example, we've seen that the sine of pi over 6 would be 1/2. However, we also have seen that the sine of 5 pi over 6 is also 1/2. This means that if I had an equation which told me that the sine of theta, an unknown angle, was 1/2, I could have more than one solution. Theta could be pi over 6, but it could also be 5 pi over 6. So we're going to always be focused on trying to find multiple solutions, right? We're going to additionally evaluate inverse trig with calculators, right? So once we've gotten a little bit more comfortable with evaluating the inverse trig with the unit circle, we're going to transcend that and we're going to go to calculators. And when we're doing this, we're going to once again need to identify multiple solutions. So you'll notice that this is kind of a common theme. And then finally, we're going to work to solve these trig equations using inverse trig functions. And once again, y'all, we're going to identify all the solutions. So let's go ahead and get started. To start things off, I'd like to take some time to once again define the trig functions on the unit circle. Remember, y'all, every trig function is going to input angles. It's going to take angles as its input, and it's going to output the following side length ratios. So that is sine of theta is the y coordinate, cosine of theta is the x coordinate. Now, let me just reiterate something real quick. Remember, guys, the idea was that around the unit circle, you'll notice there's always an x and a y coordinate for any point at any given angle. See, these are all the angles: pi over 6, pi over 4, pi over 3, 30 degrees, 45 degrees, 60 degrees. And each one of these angles has its own coordinate pair. So what we're saying is that the sine of that angle is equal to the y coordinate, right? So for example, the sine of pi over 6, as we said before, is equal to 1/2. And that's because at pi over 6, the y coordinate is 1/2 here, right? All right, let's keep going. The tangent is always the ratio of the y coordinate divided by the x coordinate. And then we have all the reciprocal functions, the ones that are flipped. Cosecant is 1 over the y. Secant is 1 over the x. Cotangent is x over y. Now, I just want to take a note here. I really, really strongly encourage y'all, keep this information easily accessible in your notes. You should be having access to the unit circle and all these ratios whenever you're doing classwork, homework, or anything, or your mastery assessments. I really am not actually expecting you guys to memorize all these things, like the unit circle or all these ratios. I just want y'all to know how to use it. Now remember, y'all, as I was saying before, multiple angles around the unit circle can give the same evaluation for a trig function. Therefore, our inverse trigonometry will often have multiple solutions within the given domain. Now, if you guys remember, domain in math means the set of all inputs which are allowed. An interesting thing that happens with domain, y'all, is that in a math problem, you will oftentimes be given a specified domain. It'll look something like this. I have two problems here. One is the cosine of theta equals -1/2 for theta within the domain of 0 to 2 pi. That means that theta can only be values between 0 and 2 pi. The other one says cosine theta is -1/2 for theta within the domain of all real numbers. This means that theta can be anything as long as it's a real number, right? Not imaginary, which is really, when we're talking about all real numbers, it basically is just saying any number you can think of. Now, to solve this problem, it's going to be very helpful for us to use the unit circle, right? Remember, guys, we said before that cosine was equal to the x-coordinate. So if cosine of theta is equal to -1/2, x must be -1/2. So what I want to do, guys, is I want to look at my unit circle and find where does x equal -1/2. And I see right here at 2 pi over 3, and right here at 4 pi over 3, I have the exact same x-coordinate. Now, because my domain has been restricted to 0 to 2 pi, I actually only need to list solutions within a single loop of the unit circle. Remember, guys, the unit circle, one all the way around, is 2 pi radian, right? So by restricting my domain to 0 to 2 pi, I essentially am just being asked for solutions in one loop. So I would give them theta is equal to 2 pi over 3, comma 4 pi over 3. Now you could, of course, give answers in degree, but it's going to be pretty common in all of your math classes in the future that they'll work in radian rather than degree. So I'd like you guys to please focus on working in radian instead of degree. If you'd like to give answers in both forms, that is totally fine too. Now, what about the one where theta is all real numbers? Well, to do this, this is essentially asking us for a general solution. We've talked about this before, the idea of a general solution. What I'm going to do is I'm going to actually have the exact same angles. I'm going to say that for this, because cosine is still -1/2, my theta would be 2 pi over 3 and 4 pi over 3. However, I need to include something to counter the idea that if theta can be anything, then I could have an angle which is, for example, one full loop, and then I end up at 2 pi over 3, right? I could have coterminal angles included here. So to account for coterminal angles, we simply need to say we have our solution 2 pi over 3 plus 2 pi k. The reason why we put 2 pi k is because 2 pi represents one full loop around the unit circle, whereas k represents how many of those loops I have done. And so that'll be my solution. So 2 pi over 3 plus 2 pi k, comma 4 pi over 3 plus 2 pi k. And once again, y'all, what we're doing is we're essentially just accounting for coterminal angles. I think that the best way for us to get a better idea of how to solve these inverse trig problems with different functions is to just see some examples. So remember, guys, sine is related to the y values on the unit circle, whereas cosine is the reciprocal of these y values. So as you can see here, sine of theta is y, cosecant of theta is 1 over y. So let's do some examples. What if I have that the sine of theta is equal to root 2 over 2 for theta within the domain of 0 to 2 pi? Well, all I need to do is look at my unit circle again and look at the fact that sine of theta, we said sine of theta was y. So I can actually replace sine theta here with y. And I get that y is the square root of 2 over 2. So where is y equal to root 2 over 2? I can see here at pi over 4 it is, and here at 3 pi over 4 it is. So I would get that my angle, theta, should be pi over 4, comma 3 pi over 4. Now what about cosecant? So guys, I'm actually going to set this up pretty much the same way I did sine there, but it's going to take a little bit more math. So if cosecant of theta is root 2, then and cosecant is 1 over y, then I know that 1 over y would equal root 2. Now, this isn't super helpful to have it in this form, 1 over y, so let's instead get it in the form of y. To do that, I need to just reciprocal it, so flip it. So I would get that y equals 1 over the square root of 2. Now, this is not quite what we want, right? Remember, guys, we like to have the square roots removed from the denominator. That's called rationalizing our denominator. So we're going to multiply the top and bottom by root 2. And we get that y equals root 2 over 2. Now, something that I want y'all to notice is that when my reciprocal function was equal to square root of 2, it was the same time as when the original was root 2 over 2. And this is just because these values are actually reciprocals of each other. And you can see I proved it right here, that they are reciprocals of one another. So actually, this equation will have the exact same solution. Theta equals pi over 4 and 3 pi over 4. Let's keep going. What if I want to work with cosine or secant? Well, remember, cosine is related to the x values on the unit circle, while secant is related to the reciprocal of these x values. So you can see cosine of theta is x, and secant of theta is 1 over x. So here's some examples. What if I have that cosine of theta is negative root 3 over 2? Well, what I can do is I can once again use my unit circle and use this ratio that we have written here. So I'm going to replace cosine with x, and I get that x. I'm replacing cosine theta with x, by the way. And I get that x is negative root 3 over 2. Well, where is that happening? Negative root 3 over 2 for the x values happens at 5 pi over 6 and 7 pi over 6. So I would just know that theta is 5 pi over 6, comma, 7 pi over 6. Once again, my domain is 0 to 2 pi, so I'm actually done with my solution. What about secant? Well, this is a little bit more tough. Secant is 1 over x. So if I take this equation here where secant of theta is equal to negative 2 square root of 3 divided by 3, I can replace it and say that 1 over x is negative 2 root 3 over 3. And if 1 over x equals this, I can once again do a reciprocal. So I get x equals 3 over negative 2 square root of 3. Now, you might be unsure. You might want to do the multiplying by the reciprocal thing here, or multiplying by the square root of 3 thing here. But what I'm going to do is actually, I want to recognize something. Guys, if I have a value, 3, and I divide it by its square root, that would be equal to the square root on top. Right? I can show you something. Watch. If I had x over the square root of x, that would equal the square root of x. Why? Because square root of x times square root of x is equal to the x on its own. And so one of these will cancel, and I'd be left with just root x. Similarly here, 3 divided by square root of 3 was equal to just square root of 3 on top. So when does x equal the negative square root of 3? Well, we just did that earlier. It equals it at 5 pi over 6 and 7 pi over 6. So the solution for this example is the same as the solution for this example. What I kind of wanted y'all to see here is that, once again, guys, even the reciprocal functions have kind of some unusual evaluations, right? That's just because they're reciprocals. They're flipped. So they look kind of shitty. Yeah, let's go with that. They look kind of shitty. But what'll happen, guys, is that you kind of can get used to the pattern, right? If I have a square root of 3 here, then I have an idea that it's probably going to be one of the values where square root of 3 is present, right? Similarly, with my previous one that I had, if I had square root of 2, right? If I had square root of 2 in my reciprocal, it was pretty likely that it was going to have to do with the other guys that have square root of 2 in their answer. Let's keep going. We're going to look at tangent and cotangent now. Finally, we have tangent and cotangent. So remember, y'all, tangent is the ratio between the x and the y values on the unit circle, and cotangent is the ratio reciprocaled. So let's see. What if I had some examples? I could have, for example, tangent of theta equals the square root of 3 for some theta within the range of 0 to 2 pi, right? Just a single unit circle. So once again, I'm going to pull up my unit circle to help me out. Because tangent of theta is y over x, what I'm going to do is I'm going to replace it with that. I have y over x equals the square root of 3. Now, what you're going to want to do is just get one of your variables on its own. The easiest one to do here would be y. So I'm going to get y equals root 3x. You see? So this one's not going to be as easy or as straightforward as the sine and the cosine ones, but we can still figure it out pretty nicely. If y is going to be the square root of 3x, then what I can observe, y'all, is that essentially y is equal to whatever x equals with a square root 3 multiplied. So if I look around the unit circle, I can see, well, where are my square root 3's? It's here at like pi over 6 and 3 pi over 6, right? Which one has y having square root 3 though, right? Notice how if y equals root 3x, then y should be the one with the square root 3 in it. And I see here at pi over 3 is where y equals square root 3 over 2. And x is 1/2. If I plug 1/2 in, doesn't that equal root 3 over 2? So I can see that pi over 3 is one of my solutions. Now, if I want to go and see what is my other solution, right? Once again, I'm going to look around for values where y is square root 3 over 2. Now, the thing with this is that I can see here at 2 pi over 3, 4 pi over 3, and 5 pi over 3, I have that y value. But which one actually will have a tangent of positive root 3? Well, it won't be 2 pi over 3, and that's because notice that the x value is negative. A positive divided by a negative will be negative, so it will not make positive square root 3. Same with 5 pi over 3. The y value is negative. A negative divided by a positive will be negative, not positive square root 3. 4 pi over 3 does work, right? 4 pi over 3 does work, and that's because I have two negatives, right? A negative divided by a negative is positive. So I know that theta could be 4 pi over 3. And that's my solutions. Something to observe here, y'all. Check it out. There's actually patterns around the unit circle for all of these multiple of solutions, right? You might have noticed by now that within a single loop around the unit circle, many of these values, many of these evaluations, right, of the inverse trig have two solutions. Tangent just so happens to always be equal to the same thing when I go across the circle, right? See how pi over 3 and 4 pi over 3 are across the circle? They're across the circle because they're a difference of 1 pi, right? Pi over 3 plus pi is equal to 4 pi over 3. Similarly, if I wanted to look at something like, say, pi over 4, right? See how pi over 4 is root 2 over 2 comma root 2 over 2? The tangent of that would be 1. So if I had tangent theta equaled 1, I would have that 4 pi over 3 is one of my solutions. What would be the other solution? Right across the unit circle here at 5 pi over 4, where negative root 2 over 2 divided by negative root 2 over 2 is also equal to 1. So in general, if I have a solution for tangent, if I get that like the inverse tangent of some value equals theta, the other solution would be theta plus pi. Let's look at cotangent here. Cotangent is x over y, so I can replace them. I have x over y is equal to the square root of 3 over 3. Now, what I'm going to do here is I'm going to actually use cross multiply. So I get that 3 times x is equal to square root of 3 times y. And once again, I'd like to get y on its own, y'all. So I'm going to divide both sides by square root of 3. What does that give me? Well, 3 divided by the square root of 3 is equal to square root of 3. So I'd get root 3x equals y. And look, it's the same as we saw with our tangent, right? So I just need to find the y value, which has square root of 3 times the x value. And that happens at pi over 3 and 4 pi over 3. And once again, since my domain is restricted to a single loop of the unit circle, I don't need to worry about general solutions or more than these two. Now let's look at what happens when we need to do inverse trigonometry that goes beyond the unit circle, right? Because we don't always have perfect values from the unit circle in our equations. Therefore, it's important for us to be able to use a calculator, right, in order to solve inverse trig. But what's more important is that we need to understand how to use the solution which the calculator gives us. So some things to keep in mind, y'all. First of all, always make sure, is your calculator set to degree or radian? This is important. You should know, right? You should be able to tell. You can look in the settings. If you're on Desmos, the default setting is radian, which is what we kind of want. Another thing to keep in mind, especially when you're doing Desmos, did you type sine -1 or did you type sine of x to the -1? These are actually different, guys. If I have sine -1 of x, that is the inverse sine. Whereas if I have sine of x to the -1, that is sine of 1 over x. Notice how the -1 is impacting the x, not the trig function. If the -1 is impacting the trig function, it's an inverse. If it's impacting the input, it's a reciprocal. Just saying to keep in mind. Kind of syntax for you guys. Now let's do some examples with our calculator. For each of the following, we're going to let theta be between 0 and 2 pi. And our first one is sine of theta equals 0.623. Now, something I want to point out to y'all, it'll be very useful to draw a picture for all of these. So I'm going to draw a picture of the unit circle. And I want y'all to remember, the unit circle is called the unit circle because it has a radius of 1 unit. So check it out. Sine is the y value on the unit circle. So what we're saying here in number 1 is that y is 0.623. Where would y be 0.623? Well, I know that the top is where y equals 1. So 0.623 would probably be somewhere around here. You see? So where on the unit circle do I have y coordinates that are that high up? I can see that I have one around here and one to the left of it, right? There's 2 values. So we need to find both of these angles. So to do it, we're going to use our calculator. If I do an inverse sine on both sides of my equation, of 0.623, what will happen is that the sine inverse and the sine will cancel each other out. And I'm left with just theta. So I get theta is the inverse sine of 0.623. Let's do this on our calculator. So I'm going to pull up desmos.com. And I want to pull out my calculator. You'll have to forgive the fact that these things are still there. But so we have sine inverse of 0.623. So to type that, I'm going to do in here functions. And I have sine -1. And I type 0.623. And you can see that I get the solution is 0.6257. And it keeps going. To be honest, guys, it'll be useful for us to just round this. Let's round it off to 0.673. How about that? We'll round up to 5. So we would end up getting that theta equals 0.673. And that's going to be this angle right here, the first one. Right, guys? So that's one solution. Now, we have a problem. My calculator didn't give me the other one, right? So how can I find the other solution? It takes just a little bit of kind of application of our knowledge of how the unit circle works with how sine works on the unit circle. But check this out, guys. Remember, over to the right, that's where angle theta is 0, right? And to the left is where theta is pi. This angle going up is going to be the exact same as this angle going up. So what I can tell is that the gap from 0 to my first angle we said was 0.673. Well, the gap from pi to my other angle should be the exact same size. This is actually an application of geometry that we're doing right now, y'all. So how do I go from pi backward 0.673? I just have to subtract them. So my other solution will be essentially just pi, which is 3.14, minus 0.673. You can evaluate this using a calculator. You can do it by hand if you like. Let's see. That would give us 2.4 and 6.7. 2.467. And that is our solution to this first one. So what you can see, guys, getting the first answer with the calculator was pretty easy. You literally just plugged it in. Getting the second answer does take a little bit more work, right? But really, y'all, as long as you have your notes and you stay focused on it, we can figure it out pretty nicely. It's just a matter of kind of applying our understanding of the fact that sine is the y value. So by using this image, right, using this diagram I drew, we could kind of figure it out. Let's go ahead and do another one. I need to reset my overlay real quick for the drawings. So now we have, let's say secant of theta is negative 1.87. Okay, so to do this, guys, I'm going to once again draw a diagram of the unit circle. Secant does not work with the y value. It works with the x value, correct? So we're dealing with x values, and it's a little bit harder, isn't it? Because we know that it's secant is 1 over x, but it's kind of hard to turn this into a reciprocal, huh? But at the end of the day, guys, what truly matters is that we recognize that we're working with a negative x value. See how x should be negative in order to create a negative here? So I know I'm working somewhere over here, somewhere in the negatives, which would give me an angle in the second quadrant, as well as an angle in the third quadrant. Here's pi. So, all right, we can figure this out, y'all. We just need to do an inverse secant. So we do the secant negative 1 of our negative 1.87, and that should be equal to theta, right? By doing inverse secant to both sides, I would get theta on its own, and I have secant inverse of negative 1.87. Let's evaluate that with our calculator. Secant, wait, where's secant inverse? Functions, secant negative 1 of negative 1.87, and we get 2.135, right? So I have that theta should equal 2.135. Now, that's going to be my first angle here. This is the 2.135 one. How do I find this guy over here? Now, there's two ways you can do it. First of all, you could figure out how big is the gap between pi and my first solution, and then deal with the same gap here. So I could do that by saying, okay, well, 3.14 minus this angle of 2.135, and then that's the gap, right? That's the gap here. And then I would just add the same gap to pi. So this gap here is equal to 1.005. So I just have to add 1.005 to pi. So my other solution would be 3.14 plus that, which would be 4.145. So that would be one way I could find the second solution. The other way I could find it is I could say, well, from 0 to the angle was 2.135. So therefore from 2 pi, which is kind of imagine, right, the full loop is 2 pi, right? So if I go backward from 2 pi, right, by 2.135, I could also get the answer. 2 pi is 6.28. 6.28 minus 2.135, what's that going to be? It'll be 5, 7, 4.145. Oh, look, it's the same exact answer. So this is kind of the way in which I personally solve these inverse trig problems. I'm going to do one more example with this to kind of continue getting us on the right idea. By the way, y'all, the way that I solved this secant one in the diagram looking at the x values is the exact same thing I would do with cosine. Similarly, when I did the sine and I was working with y values, I would do the same exact thing with cosecant, where I'd be working with y values as well. So one last time, we're going to reset our board. And let's do tangent of theta equals 5.14. So once more, y'all, and I'm going to do it big this time. Once more, we're going to do our diagram. Tangent's odd because tangent is y divided by x, right? So it's a little bit weird to work with tangent, but we can see what happens. So to find theta, I just need to do the inverse tangent to both sides. And let's see what we get. Go to Desmos. I do in my functions tan inverse of 5.4, and I get 1.387. I'm going to round this up to 1.388, right? So I have that theta is 1.388. Where would that be in my unit circle? Well, remember, guys, here's 0, here's pi. Pi is 3.14. This guy's less than half of pi. So it's somewhere around here. Essentially, pi is 3.14. Half of that would be like 1.57. And so it's somewhere between 0 and 1.57, right? Now, tangent had that interesting property we were looking at before. Because tangent is the y divided by the x, its second solution will just be right across the circle from it. The same thing can be actually said for cotangent as well. So right across the circle is where the other solution will be. So actually tangent's really easy to do because all you have to do is take your first solution and add pi to it, right? See how across the circle is plus pi? So I just take this answer and I add 3.14 to it. So 1.388 plus 3.14, what will that get me? It'll get me 8, 2, carry the 1, 5, 4.528. And that will be my two solutions for this. So what I hope you guys have seen in this section of the kind of asynchronous video here is that finding the first solution for an inverse trig problem is actually not very challenging. It's not too crazy. It's pretty simple to plug it into a calculator. Finding the second solution or the other solutions is a little bit more tough, but by drawing a diagram and keeping in mind our idea about the ratios, maybe make sure that you have in your notes written somewhere about how we were able to solve this second value for tangent, right? If tan, essentially guys, tan theta should always be equal to tan theta plus pi. This is always the case. This is always true. So it's kind of a cool little thing. Cool. So we're going to go ahead and move ourselves forward to the last little bit where we're going to work on solving the final trig equation. Let's get it. So now that we have an idea of how to evaluate kind of the more simple trig equations, let's see what happens in a more complicated equation. For example, I have the one that we saw before. We have 3 times cosine of pi over 4 theta plus 5 equals 4.68. Now, I want y'all to take note here. Our goal when we're solving these trig equations is going to always be to get the trig function on its own. That way we can just do the inverse trig and it will function the same as we saw just before. So actually, guys, it's not too crazy. what I'm going to do is I'm going to view cosine as a single entity, and everything within it is contained within that box. In reality, what this equation says is basically like 3 times x plus 5 equals 4.68, where x is our cosine function, cosine pi over 4 theta. But so you can see it's actually not too hard to get cosine on its own. It's just like basic algebra. We're going to subtract 5 from both sides. And we get 3x equals negative 0.32. And then we're going to divide both sides by 3. So x equals negative 0.167, right? I did that wrong. Oh, well. 1067. You could do a calculator to do these things. So essentially, guys, what we've found is that cosine of pi over 4 theta is negative 0.1067. So how do we undo cosine? Well, we simply use an inverse cosine. So we'll have pi over 4 theta equals the inverse cosine of this value. Hang on, let me erase this stuff out of the way. Negative 0.1067. All right, so we just need to evaluate this with our calculator. Let's get it. Cosine inverse is right here in the functions of negative 0.1067. That will give me 1.68. We're going to round it to 1.678, I mean. So we have that theta. Actually, not just theta, guys. What we have here is that we have that pi over 4 theta equals wait, what was that? 1.678. I'm going to quickly erase this other stuff around here in order to give ourselves some more space. Let's see. How can I do this? How can I do this most efficiently? There we go. There. So what have we gotten? We've gotten that pi over 4 theta is 1.678. Now, I'm going to quickly draw our little diagram here, y'all. Remember, when I look at the unit circle, guys, cosine is the x-coordinate, right? Our x-coordinate that we were looking at was negative 0.1067. So it's kind of barely to the left. So it's up here and it's down here, right? So we're looking at essentially x-coordinates. We're looking at angles, which are this one right here, and you can see it was 1.678. From 0 to there was 1.678, and then this one down here. So the way I'm going to find this second solution, right? The second solution is I'm going to look at, well, right here is 2 pi if I view it as the full loop, and I'm going backward by 1.678. So I'm going to take 2 pi, which is 6.28, and subtract 1.678. Remember, y'all, pi is 3.14. So if I have 2 pi, I just double it, and I get 6.28. That's what I'm doing when I'm doing this. So to get this second solution, we just subtract them, and let's see what we get. We get, got to carry it over. I get 2, 0, 6, 4.602. 4.602. Now check it out. Am I done with it? Have I gotten theta on its own? Have I solved for theta? In reality, guys, I actually haven't, right? Do you know why? Because I still have pi over 4 attached to it, right? So all we have to do is then, and this is going to be saying where, let's use our calculator for this, okay? We just have to multiply everything by the reciprocal, 4 over pi, right? Because that'll cancel out here. So if I take these two solutions and I multiply them by 4 over pi, I will get my final answer. Let's do it on the calculator. That seems a lot easier. We had 1.678, and we're going to multiply it by 4 over pi. And then our other one was 4.602, and we're going to multiply it by 4 over pi. So my two solutions that I get are 2.136 and 5.859. That is theta. Oof. That didn't turn out so pretty, did it? In the way that this thing, yeah, there we go. Now we can see it nicer. So our two solutions were 2.136 and 5.859. So to recap, guys, what is it that we did to actually solve this? What is it that we did to solve this? All right, let's see. We essentially isolated cosine. So we subtracted 5 from both sides, and then we divided by 3. So then that gave us that cosine of pi over 4 theta was equal to this decimal that we had before, which I'm not going to calculate again, actually. Oh wait, I remember. It was like 1 point something, right? 1.06 or something like that. We used an inverse cosine to get rid of cosine. So we said pi over 4 theta was equal to the inverse cosine of 0.106. Determining the two solutions for this was kind of the hardest part of this problem, right? But eventually we did it, and we had that pi over 4 of theta was equal to those two solutions, something like 2.5 or something, and like a 4.3 or something like that, right? And then finally, we multiplied by the reciprocal of pi over 4 because that allowed us to get theta on its own. And we do it to both of them. And we ended up with our solution for theta. I hope that this lesson today, I know that the material is a bit challenging, but I hope that it's not too challenging. And I hope that this has made some sense. If you find that you're still confused about these problems, I might suggest re-watching some of the solutions over again. I think that oftentimes it can be hard to understand the solution fully until you've seen it a couple times. Additionally, guys, the best way for you to learn these things is to try it yourself. Okay, the best way to learn math is to just do it yourself, try it out. Honestly, guys, it might be a worthwhile exercise to try doing the exercises, the practice problems that I did myself on your own. So once you've seen this solution, you can do it on your own as well. You know what? Screw it. That's going to be part of our asynchronous, the notes check, is to do these on your own as well. All right, so let's recap what it is that we did today. During this assignment, we evaluated inverse trig with the unit circle and identified all the solutions. We evaluated inverse trig with calculators and identified all those solutions. And then finally, we solved some trig equations, right? We solved a trig equation using these inverse trig functions, and once again identified all the solutions. It's a lot of solving, it's a lot of trig, it's a lot of solutions.